capability of my computer. So, guys, thank you very much for attending. My name is Yuri Reznik. I run a research team at Brightcove, and the topic today will be actually quite research. I will use some formulas. I have to give some warnings ahead of time. Don't be scared. But I'll try to interleave it with some more casual words, so hopefully it will be understandable at multiple levels. And the topic is on ABR streaming and CDN performance. And it works good. So before I jump into substance, let me just review a few things from history. Just try to refresh our memories on how we even arrived with streaming concept as such, and why things been designed the way they were designed. And first thing to note is that streaming was actually not the first way media was delivered over IP. Video phones were there decades before. And actually, things like H.324, H.323 stacks existed at about the same time when people started playing this concept of one-way streaming, and there were guys like VideoNet and others who were trying to use H.263, H.324 one-way, and it actually didn't work well. And there were reasons for this. Those were low latency protocols, and if you try to do streaming over 28K modems or 56K modems at that time, that latency was a very precious luxury that you could take and accumulate bits and use it for retransmissions and fix your errors and achieve better quality as a result. So first successful systems, they were all UDP-based stacks. They used H.263 derivative video codecs. Speech codecs were used mostly for audio, and the names are here: real audio, real video. I actually used to work at Real Networks at that time, so those were my babies. Vivo Active, it was a company of Bernd Giraud, Stefan Eriksson. VXstream, that was acquired by Microsoft. Of course, Microsoft themselves with NetShow as their first entrance in this area. Of course, it was done over UDP. Things were much more challenging at that time. 28K modems, as I said, was the reality. And try to send video to such connections. Then came adaptive bitrate system. So ABR system didn't came with Dash, it didn't came with HLS, it didn't came with Move networks, as many people believe. It actually came over a decade earlier. It was invented in 1998. And first streaming system of this kind was actually Real System G2. The adaptation algorithm was called SureStream. And as I show on this diagram, it's a picture of real producer with kind of selection of target audiences, where you could click 28K, 56K, like single SDN, dual SDN, and so on. So this was the means by which encoding profiles were created back in 1998. And it worked. Of course, it was designed differently. It used UDP. It was patented. I'm embarrassed to say that I was one of the co-author of this system. But later, actually, what I discovered is that what was invented was novel in a way how multi-rate encoding was used. We encoded video and audio at multiple streams, and then we were dynamically selecting them. But the sheer fact that video and audio could be encoded in multiple streams, it was known earlier. In fact, in wireless telephony, there already existed several so-called multi-rate speech codecs. It all goes to half-rate GSM codec and later AMR family, and as well as in 3GPP2 there was VMR and AVRC type codecs that were designed to operate at multiple bit rates, and systems were subsequently designed to adaptively switch between those rates. So what was done for streaming was novel in a sense that we did the switching after encodings was done. but the sheer concept that you could encode at multiple bit rates and switch dynamically, it was known before. And of course, why would you do the switching? Well, you do switching mostly to accommodate for changing conditions in network. If you stream over the network and all of a sudden there is a congestion somewhere, you can't maintain continuous playback. You need to do something about it. You could switch to lower bitrate stream. Hopefully that will give you enough of bits and you still have bits in your buffer such that you can continuously play some content, maybe not at the same level of quality, but at least continuously. So that was the underlying idea. And in the original system, the entity that was doing adaptation was actually a streaming server. It was selecting those streams. It was receiving information from the client, telling it which bandwidth is observed on the client end. And the reason it was that bandwidth detection was estimation was done at client was actually latency. Initially, we tried to do it on the server side, kind of trying to look at the retransmission requests that were coming back to us. But since all those things were coming over UDPs, there were round-trip delays, and it was just faster to do it on client. So that's how it went mostly to client. But what also is important about this system is that past server, everything that goes over the network is a single stream. You decide which stream you send. You don't abuse network anywhere else with anything else. You send single streams that the client needs, and that was the beauty of it. That's how it was intended to be used. But it wasn't scalable. That's really what, and there were some other, of course, painful things about it. For example, it was UDP, your packets were lost, so you need to deal with error concealment. It was a pain in the neck to handle all those things. But the weakest point was actually server. It was okay to stream, say, 1,000 events on a single piece of hardware, but if you needed 1,000 streams, but if you needed 10,000, 100,000, well, it was challenging. So back in early 2000s, we started building proxy servers, content networks for UDP-based streaming, but it never really was well designed and as simple and elegant as later solutions that came after this, which was HTTP-based streaming. And of course, the credit for this goes first to Move Networks back in 2007. That's the first company that came out with concepts, and Apple did HLS. And if we look at this system, it looks similar to what I was describing before. The streaming client does estimation of what bandwidth is available. It decides which segment to pick. So the difference is that things are encoded in segments. But the biggest difference is that there is now a CDN here. There is origin server, of course, which is now a typical HTTP server. It doesn't do anything intelligent. But then it's connected to CDN, and CDN does the scaling. And what CDN does as part of its scaling, of course, it operates a plurality of edge caches, and each edge cache looks at the content. If it has content locally, it streams it right away. If it not, it asks it to be propagated to it from origin server in the worst case. So that's the basic concept of HTTP streaming. It simplified the problem of scaling because CDNs could be used, and CDNs were designed to do this. But there are some things that came with this, and I'll talk about this later. So it works very well when you need to scale delivery for content that is popular. Why? Because if it's popular, it's going to stay in cache. If it's not popular, it's not going to stay in cache, and you're going to actually go all the way back to your origin and pull it. The only difference will be is that you're going to pay not only for the bandwidth that you deliver through CDN, you also will pay for MIDGRESS to get it from it. So for popular content, it's best things creation. For non-popular content, it also helps. Why? Because CDNs usually have better backbones and can propagate content faster across different continents, for example. But technically, it's not as wonderful and simple as in case where the content simply sits in cache. And now, let's look at this picture again, and let's try to see what is happening here. Basically, if we would be streaming just single stream, we encoded it at 1 bit rate and we're pushing all the way through CDN, it would be wonderful. CDN, if content is popular, CDN will cache it, we'll send it further. But we are not sending single stream. We're actually sending a whole bunch of them. Why? Because different clients, different devices will have different constraints. Some will be able to pull 1080p, somebody will stack at 360p, some will be stuck at 720p. And they will all be competing for same cache storage at the edge of the CDN for this content to be present there to get it fast. If it's not there, it will go all the way back to the origin. So that's where I see the disconnect between the original concept and what is happening with CDN. And of course, what happened with streaming recently, it actually got abused. So the concept of HTTP streaming got abused in the sense that not only we have multiple encodings now, we also have multiple formats. People package things in Dash in MP4 files, they package them in HLS, and in HLS several versions of it. There is also a variety of CDNs, I'm sorry, not CDNs, DRMs. For some legacy devices, you still need to use smooth. Sometimes you still need to do progressive, but that's a whole separate story, right? And again, that creates extra space of different formats that are hitting CDN cache and basically killing performance of the system. And last thing is actually things getting only merrier with new codecs. Because why? Because there is MPEG saying that, hey, we have a HEVC that is more efficient, please deploy it, right? Then there is Alliance for Open Media saying this is AV1, please deploy it. Well, reality of it, you cannot deploy new codec in a way such that you disconnect and terminate all streams that existed with old codec. You need to maintain everything that was before, and then you add a new codec on the top of it. Where it goes? It goes to CDN edge cache. And those new formats, again, fighting between each other for whoever's going to survive there. So that's where I see fundamental disconnect between the model and what we actually have with CDNs in terms of performance. So effectively, ABR streaming says more is better. CDN says less is better. So we need to find something in between, maybe. So now there is going to be some mathematics. I warned you about this before, but it's actually fairly simple. And
there's more pizza.
So let's try to figure out what's going to get cached in CDN. And let's consider, for example, that we have just a set of items. I call them SX, just items. It could be segments, it could be video items, doesn't matter. From mathematical standpoint, it's just elements of a set. And we have some popularity model that associated with this. This is actually a classical zeta distribution, which is, again, it's a discrete variety of so-called pair 2 distribution, which is very commonly used for measuring popularity of content in a variety of natural settings. For example, distribution of words in English letter is a well-known example of using it. Distribution of popularity of clips on video clips on YouTube. There was a paper that said that that model fits very well. And just following the tradition, let's assume that that model is good enough. And by the way, it has a parameter, which is a parameter alpha that allows us to tune it to fit actual experimental data. So there is a degree of flexibility with this model that allows us to get to realistic data when we need to match them. Now, what's we also need to assume what is the capacity of the CDN cache. Well, let's assume that the cache can hold C items. And if cache designed ideally, what those C items will be? This will be C most frequently used items out of that set. So we basically take like X most popular items, they have highest probability. That's what we assume cache will store. Well, if that's the case, well, we can compute probability that things not going to be in cache. And that's going to be just 1 minus sum of everything that fit in cache. And that becomes pretty simple expression where there's a harmonic, generalized harmonic number, but it actually has a asymptotic expansion, which is even simpler, which is basically says that it's a capacity. So the probability of miss is going to be proportional to, inverse proportional to capacity of this cache with certain power factor divided by function of the parameter of distribution. Very simple model. It's intuitive. We can work with it. And what we can do with it next? Well, now let's see what's going to happen if we have two versions of same content. It's the same cache, same capacity C, but instead of one set of items X, right, Sx, I have two sets. One is S subindex 1 and the other S subindex 2. Well, what I also need to know is what is the relative usage probabilities between them. For example, one version is used in 25% cases and the other used in 75% cases. So let's denote this by P, P1, P2. And let's see what's going to happen. Well, if we know the usage probabilities, we know popularity probabilities of content by itself, then the full probabilities in terms of what is relevant to CDN will be products. And then if we look at the top a few items of what's going to stay in cache, what I really need to do is I need to sort those products of probabilities in order of their decay. And what I discover, well, assuming that P1 is greater than P2, is that that will form an interleaved pattern. So I will have first coming items of most popular, most used content. Then I will have first element of second type. Then again, for a continuous chain of from first type. Then again, second. So there will be interleaved sequence of those items where the items, the version that has higher usage probabilities will be present more prominently. That's what it really means. And if I observe this fact that there is this type of presence, then I could express what? I could express probability of cache miss in case of second. In case of two formats, it becomes this expression. It's a very simple math. And I can compare with first one. And how I compare it, I will look at the ratio of them. And if I look at the ratio of these two things, what's going to happen? The final formula that I obtain is no longer dependent on C, which is capacity of the cache. So what I discovered is that, if you do some asymptotic assumptions and you look at the ratio, relative ratio of cache miss probabilities in case of single format versus two formats, then it converges to something stable that is no longer related to the actual cache size. And if that's the case, then for any reasonably large CDN, what I could say is that the ratio of cache miss probabilities will be described by this C. I can plot it. And what it shows that basically if both formats are equally probable, we stay in the middle, then the impact on cache miss will be the most significant. So if you try to push two formats over CDN and one is not used at all, this is wonderful. It's not gonna mess with the other contents, it's gonna stay there. But if you're gonna push two formats and they are both equally equal, that's where they start fighting with each other. That's where you're gonna have this very significant impact on the cache miss probability. And basically the answer here is don't do this in practice. If you want to have high CDN performance, try to push something that has as asymmetric distribution as possible. That's, yes, please.
Say that again. You're not saying don't use multiple formats. You're saying use unpopular ones?
Basically do this. figure out which format is most popular and route as many players to use just that format, and make the other formats as least probable as possible. If you have one format that is dominant in terms of usage probabilities, this is good for CDN. That means that that format is more likely going to be cached. That means more likely more players will be able to use it and more customers will be happy with it. So yes, please.
Would you explore taking this to inversions of the same content?
This could be done for arbitrary number of, so it's a similar extension. It becomes a sum of, what you see here is actually LP norm of the usage probabilities. So for n, it becomes a LP norm for n of them. So that's a very simple recipe we arrived at by just doing very basic mathematical experiment. And now let's take a look at some examples of practical scenarios where we could immediately try to apply it. And one wonderful situation will be when to deploy HEVC. It's very pressing for some question in practice, and so let's assume. So let's think that R is the rate of H.264, delta is the rate savings of HEVC. Let's assume it's somewhere between 1/4 to 1/2. Of course, standards committee says that it is 1/2 and even more. People in practical community says that it's more 1/4. Let's think it's somewhere in between. P percentage of devices that can play HEVC. And alpha is the shape of content popularity distributions that we discussed before. Then, using those things and also things that we've derived before, we can express a few things. We could say what would be the total amount of storage that is required for storing both HEVC and H.264 streams, right? What would be the average bandwidth that is used? And this is very easy because we have percentage of devices using HEVC, so it becomes a just blended average using that pi as a percentage. But then what would be CDN cache miss probability? That's where that formula comes in. And that's the expression that is essentially the most non-trivial in this exercise. And now let's take a look what would be happening with CDN cache miss probability if we just have different rate savings of HEVC, which is delta, and different reach probability, which is pi. So what we see is that there is a region, which is this triangle showing, where HEVC will actually reduce the cache miss probability. But to hit that region, you need to have, if you're saving 50%, you need about 82% of devices supporting HEVC to be in that region. That's what this mathematics says. That's just cache miss probability. But you will say that cache miss probability is not a true indicator of total costs, right? This, it just indicates at which point deployment of HEVC will be breaking even if you don't have any caching at all, if you're streaming extremely non-popular content. But if you're streaming popular, it's probably different story. So let's take a look at overall traffic cost. So the overall traffic cost is going to be this. It's going to be traffic that cost we're paying at edge for traffic going from edge plus cost we're paying for MIDGRESS. It becomes a blend of those two. And plugging in the formulas that we've seen before, we can show this. If we do have a situation where the MIDGRESS traffic is much more expensive, which is the case with many CDNs, then the ratio of total cost of sending H.264 plus HEVC over HEVC boils down to this expression. So this Xi, which was our fraction indicating the change in cache miss, is just one factor. The other factor is 1 minus P delta. And if you plug this, it actually becomes a more favorable for HEVC because the area where we start seeing gains is much broader, and even if rates is savings at 25%, hitting about 1/3 of devices becomes sufficient, such that if you look at overall CDN costs, you will start breaking even. So that's basically the mathematics that describes the trade-offs in this case. Another case, and the last case that I will consider, it's another popular topic of the day, is when it makes sense to deploy CMAF. It's a new standard. There is much hope that it will drive conversions of both DASH and HLS in industry to a single format, which of course will help CDNs to achieve high performance. But the problem is that if you try to deploy CMAF today, the way you can deploy it will be additional. You will still need to support devices that can only play HLS as HLS devices, and so it gives them an option to load HLS devices that can play DASH devices, play DASH in whichever flavors they support, and then CMAF comes third. So from that consideration, what we really have mathematically here is a comparison of 3-format systems versus 2-format systems. And you would think that probably 3-format systems will never be better than 2-format systems. You're adding an extra format, how in the universe it may help CDN performance? Well, if you remember, when I did my initial exercises, I showed that if you have a single format that becomes dominant, that actually helps. So what I'll show in a few last 2 pages is that if we have sufficient number of devices that will be able to support CMAF, that becomes the point where deploying it will actually start saving money right away, even considering that you still need to support HLS and DASH devices by themselves. So these are cache miss probabilities in both cases, in cases of 2-system and 3-format systems. Actually, I think I screwed up. This shouldn't be here. But that's all right. So the first one is just takes 2. The second is row, where rows are usage probabilities in case of 3 formats. Then let's also assume that when CMAF is deployed, there is a kappa, this funny letter, that represents a percentage of both HLS and DASH devices that will be able to switch and decode CMAF right away. So a kappa is basically percentage of devices, of existing devices that will be able to take CMAF. And then what will be probability of CMAF is basically it will be kappa times P1 plus pi2. Then the residual probability of devices that support, for example, only HLS is going to be 1 minus kappa times pi1, and residual number of devices supporting DASH will be 1 minus kappa pi2. So that's how it works. And then we could just compare cache miss probabilities in case of 2-system versus 3-system, where in case of 3-system we use this raw probabilities that are shown here. By doing a little bit algebra, it becomes equivalent to basically looking at this inequality where the parameters are now kappa, alpha, and pi. And basically this is what it boils down to. So kappa here means a percentage of devices that can play CMAF. Pi is a trade-off between existing HLS versus DASH devices. And again, the 0 is a plane where those probabilities will be the same. So if it goes down, it means that CMAF is actually allows us to reduce costs, and it allows us to reduce cache miss probabilities. And so that region becomes well characterized in this case. And doing some plugging of ballpark numbers such as 1.16 for the decay of the popularity distributions, and assuming that, for example, 75% of devices use HLS versus 25 use dash, we arrive at wonderful factor deployment for CMAF, which is 0.084, that is needed to make that standard successful. Few mathematical exercises with some consequences for some known problems. So,
Yuri, sorry to interrupt. So, if you go back, so with kappa calculated to be 0.84,
yes,
is the interpretation that 84% of devices
should support CMAF, should be CMAF capable for it to hit, to have same cache miss probability as you have now with two formats. And this might sound like a high number, but if you consider the fact that you already have two formats and you are now adding third on the top, that's where it really becomes much more harder barrier to go over. So that's the minimum density you need to hit to make it worthwhile economically. Conclusions. Simple model proposed, several examples given, but it's actually, I think, it's just the beginning. If you remember when I started talk, I was talking about how ABR streaming was designed to begin with and what the objectives were. And in my view, the addition of CDN happened in somewhat ad hoc manner without due thinking about how this should be done optimally. And perhaps if we think deeper about it, if we use models and understanding of what actually will be cached, what will not be cached, what the impact of that will be on network bandwidth distributions, maybe we can design systems that works a lot better than what we have today. Thank you very much.
Does anyone have any questions that they want to ask? Are you going to stick around?
Yeah.
Okay.
So you know.
How far are we from the 0.84?
My sense is that first, most Apple devices already support it. And some TV players, some smart TVs also can play it back. So it really depends on operator. It really depends who you're talking to. If you're talking to somebody who is streaming predominantly to Apple devices today, maybe he is already crossing this line. Keep in mind that those distributions, they are not absolute industry-wide. They're always specific to the context of each particular customer. So overall, if you think all platforms together, of course, we are not quite there yet. So what I know is that CMAF, support for CMAF was added in some late builds of Chrome, but how stable it is, I do not know yet. But once that is stable, that of course will cover a significant portion of desktops. And of course, Android will be the last thing that at this point I just don't know anything about. So.
MPEG is also looking at relaxing restrictions on what CMAF is defined by, such that the ICP left segments for dash qualify as CMAF.
Yeah.
So that would automatically enable most dash clients to make.
So I honestly think that CMAF is the best thing in a while that is happening now, and especially considering everything I was saying before, that basically the less is better from CDN perspective. So driving that commonality is, of course, a big deal. The question is how to get there. And how to get there without breaking everything that exists already. That's where the challenges are. That's where the initial deployments will be facing trade-offs, and you need to design systems that is more complex than ideal single format system in the end.
Great. Yuri, thank you so much.
Yep.
So I'm just going to switch presenters now.
Is it? It's on? Good? Okay. Oh, there we go. Okay, great. So I'm Jason Justman. And a few familiar faces, Andy, Aaron. I currently live up here in Seattle. I work for Sinclair Broadcast Group, but just as a very quick disclaimer and disclosure, what I'm going to talk about tonight does not necessarily represent the views of Sinclair Broadcast Group or One Media. Just want to get that out of the way. Toaster Flyer, and then upgraded to a Media 100, which was data translation back in the day. So if anyone goes all the way back to dealing with component Betacam SP, I probably played around with it, but it gave me a really good foundation to understand some of the use cases and challenges that broadcasters have on a day-to-day basis and how the industry is changing and how that's challenging. So the big piece that comes along together, and what I've noticed is that traditional broadcasters are very focused on hardware and infrastructure and transmission, right? These are things that software people, we've gotten really good at not having to worry about those things anymore. There's so much that great partners like Bitmovin do in the marketplace that we don't really need to run any infrastructure, and we don't want to run any infrastructure, right? If we have to spend any CapEx for physical infrastructure, it means we are severely limiting our ability to be agile and flexible in the marketplace. So what this all comes back to is really looking at how the industry innovates for broadcast, for media, for digital. There's kind of this convergence point that's coming together where we have OTT is really, really a big player right now. But in the future, what we think potentially is there's going to be this convergence between OTT and OTA. So traditional broadcasting for the past 20 years have been transmitting their content on a technology called ATSC 1.0. It was very, very innovative at the time, and it started coming out right about 1997. And it was the pinnacle driver from moving from analog transmission to digital. Now, most of us were probably still in high school when that happened, or younger than that. So we don't really understand the impacts of how painful that was to the industry to do that. Now, what I'm giving you are some quotes from the ATSC organization about ATSC 3.0. I'm not going to talk about what happened with 2.0. But it sounds like there was a lot of challenges in between there, and so they just decided to move forward. But what's important to note here is that it's a suite of voluntary, right? Traditionally, broadcasters have to adhere to the policy and regulatory compliance from the FCC. We are in the public trust. We have a responsibility, therefore, we have an obligation not just to our audiences, but for also ensuring that we are in compliance with with the RF side of spectrum management. Again, this goes back 100 years ago when RF meant that people were winding coils at specific densities and radiuses and lengths because that's how oscillators worked. And if you had a transmission that was noisy, you would interfere with other people. The transformational part of how this works is that we no longer have to worry about that. There's things and technologies in place, it's called software-defined radios. What it essentially lets you do is to be able to pick out any frequency in a marketplace. It takes a broadband capture of it, applies really, really intelligent algorithms, and from this one little USB device, you can scan from, I usually do a scan when I go into a market from 470 to 800 megahertz, and it can pick off a 10 megahertz channel window up to, I think it's about 100 megabits a second of analysis data.
Hey, Justin, how much does something like that cost?
So these are still very early on in the research and development phase at that bandwidth. The Airwaves device, which is actually made by a company in Newcastle, Washington, this device is about $1,000. This device you can't buy. But the same idea is that if we can dynamically program spectrum utilization in a marketplace, all of a sudden now we have, as a broadcast community, there are so many new opportunities to be able to extract value out of it. Traditionally in ATSC 1.0, they made a very conscious decision to only support a transmission model called ASI. So ASI went from the station to a transmission link, and then from that transmission link, essentially it would be MPEG-TS and MPEG-2 video. So very, very efficient back in the late 90s. But today, it's absolutely a waste of that resource utilization. So as a broadcaster in the US, when you serve a market, you get a 6 megahertz channel. And usually that's all you get. So when you watch TV now, there's been iterative innovation to go from one HD channel to one HD channel, 2 HD channels, and 3, 4, 5 other supplemental channels. It's a piece of technology called Statistical Multiplexing. Originally, that was really, really interesting because it allows you to extract more value out of the capacity you have. But at the end of the day, you had a finite limit because you're stuck with old codecs, and traditional broadcasters are not flexible because they are stuck in this ASI signaling format, and there's very few things you can do. So the important part that comes out of this is this last sentence. It's kind of misrepresented. It's not largely incompatible. It's completely incompatible, right? So what this really kind of means is, like, from a broadcaster, nothing is going to work, right? But you know, there's this idea called the diffusion of innovation. And in this use case, and I'll help to elaborate this a little bit more, we are like right on here. ATSC 3.0 has only been deployed technically in one market right now, that's Phoenix. They are very, very excited about it. And when I say they, I mean the hardware guys. The people who manufacture the encoders, the modulators, the exciters, the towers, and the consumer electronic devices that are very, very expensive, right? Who here in this room works for a company that does something in that portion of the supply chain?
Subcontract?
Andy, you're an exception. But my point is that there's so much technology that's built into here that is just absolutely innovative and amazing. And as I walk through this, I'll show you a little bit more. But there's a fundamental miss and gap about how the technology is moving forward at a very quick adoption, but it's all in the hardware and infrastructure side that we don't really care about. I like to say the technology is the facilitator, but ultimately the content and experiences are the differentiator of what's going to drive new technology and adoption. So, you know, I've heard these statements before again about how, this is going to offer so many improvements that it's going to just be a game changer, right? It's going to offer a better performance, functionality, and efficiency. But you have to go back to that core covenant is nothing works, right? Non-backwards compatibility. That's a very, very risky subject because as a broadcaster, you have to reach those audiences because you have that spectrum. If you don't reach the audiences, guess what? You get that spectrum taken away. So it's kind of sensitive and it's a challenging position to be in, but what essentially it feels like, because we've been talking about this for the past 4 years, maybe 5 years of ideation, right? Is that every year there's CES, and then 3 months after there's NAB. And we go through this oscillation where we get really excited about this, and then we're like, where is it, right? And so from someone who crosses between those two paths of the hardware and the software side, I've waited almost 4 years to be able to say, when can I see this working? When can I actually touch a data transmission? When can I write code against it? Because until I have I have a contract interface with the ATSC 3.0 specifications, but until I actually get a byte of data coming through this device, because remember, this is just a receiver. Without a transmitter, it's moot. Like, you can't do anything with this except say, I have a $1,000 piece of hardware that I can't do anything with. Now, the great thing about ATSC 3.0 is that this is not a greenfield exercise in the US marketplace. Korea deployed this out for the 2016 Olympics. Is that, yeah, 2016 Olympics or 18? Forget, the 16, yes.
For the Olympics.
Yes, for the Olympics. But what essentially is they innovated this technology with Samsung and LG to execute this and with SKT as a government initiative to showcase the capability of Korea. It just so happened that this as a broadcast technology worked way better than the traditional ATSC 1.0. And it was a substantial enough improvement on the RF side that it superseded things that like Europe with DVB-T2 or ISDV. This is just so phenomenal. And one of the pieces that comes out of that is that Korea is a few years ahead of where we are today. So between this and this is a modulator for ATSC 3.0. Now, everything I need to represent a broadcast transmission facility is right here in my hand. This is really, really exciting because for people who cross over between the hardware side and want to build applications and experiences, now I've got a real infrastructure to work. So we went from this trial disillusionment for years, and now it's like there's a little bit of enlightenment. And I'll walk through this here. But the big challenge that comes in is that, scenarios like ultra high definition services. In Phoenix, one of the use cases that I happened to watch last night is it was streaming over one of their broadcast channels, 4K, HDR, with AC4 audio codec, right? This combination and permutation is really, really hard to do at scale because you're talking about maybe moving 15 to 20 megabits. The amazing part of this, it means that they're sending out one copy of this. They're not sending out tens of thousands of copies like a traditional content delivery network would to reach that audience. Just leave that one to think about this, right? So when people talk about, is it going to be ATSC 3.0 or is it going to be 5G, we think it's going to be a hybrid because while bigger pipes are better, we have to start leveraging smarter pipes. There's a model in here somewhere that says if I have to move 20 megabits of video to Andy and to Darren, and then a third person comes in, we're all in the same room. Why do I need to send you each your own copy at some point? And there's probably some interesting business models that come out of it, but again, we go back to that big question of why am I going to throw everything away is because this word right here, IP transport. The really, really dumb thing that happened with 1.0 is a proprietary protocol and encapsulation format. The really, really smart thing with ATSC 3.0 is it's all IP multicast. And that means there's 25 years worth of technology and software to support moving bits and bytes. So when this all comes together, essentially about 8 years ago, it started with the realization that they were getting themselves locked into a corner back with what's called the Grand Alliance. This was when they first came up with, they were fighting between what's called 8VSB and QAM. So 8 vesidual sideband is, they're radio oscillations, there's certain carriers that oscillate through, and then there's QAM, which is a constellation model. Again, back in the mid-90s, those were so innovative because previously, and I don't mean to go into too much technical detail, but it was either frequency division multiplexing, time division multiplexing, or CDMA. And so FDM was those original analog phones that you had where if I made a phone call, it would be at this carrier and pilot. Time division was the first piece of getting the quantization so that way multiple people can be scheduled on it. And then code division multiplex access was the first utilization to establish a wideband channel for this. Now, again, just from a high level, the way that this works is that technology's advanced so far is what we're able to do is granularly control all 3 of those variables. We can control the frequency, the time, and the modulation to the point that is down to essentially the lambda oscillation, which is really, really interesting, and we can do it in software. So what that means is when we start building these networks out, it is what we call a single frequency network. And the single frequency network is such a granular point of control that we can emit what's called a bootstrap, which will identify the preamble for data transmission. Now, it sounds super complex, but what it means is now any device can wake up and receive that from the bootstrap signal and be able to process that data if it's relevant to it. And the data it's processing is IP. So if you have ever worked with AWS IoT, this was a great deployment of a pub-sub model. When you start thinking about that, this is exactly the same use case. Now, I thought we were going to talk about video, right? So this has absolutely nothing to do with video. This is with RF engineering. This is with payload encapsulation. This is with division frequency and time division multiplexing. All these things that the only people who probably really care about this would be double E's who went to school, right? And then we've got this different model of layer division multiplexing, which means that different towers in the single frequency network can have the same core payload, but then modulate on top of the waveform separately. And then we have all these exciting things about constellations of QAM and different carrier capacities. And then we get to the structure of the transmission system where it goes through multiple timings. And again, this is all in software now. And then we get into the ability to fragment that 6 megahertz channel up into multiple physical layer pipes in a virtual channel, so we can have different modulation schemes based upon the transmission and durability. But where this all comes together, which is really exciting, is they did not overlook video on this. Essentially, everything in ATSC 3.0, and the discussion earlier was great because it's all ISO BMF. Everything that's delivered over ATSC 3.0 is leveraging essentially that same statistical multiplexing model just at a massive scale. And not just for the content quantization, but also for the distribution of that data. The reason that this is super important and why the 5G versus 3.0 and why this is the right decision to make goes to one last piece of scientific exercise. So back in the 40s, the Bell Labs, the old telephone company, had a research division, and there's a brilliant engineer called Claude Shannon, and he came up with this model that said that in a noisy communication channel, there is an upper bound of what you can transmit in that channel. This is the black, that's called the Shannon limit. This curve on here represents that. This is, because of all the degrees of options that you have in transmitting a signal in ATSC 3.0 from the RF side, this is probably the closest we will get to getting to the Shannon limit, which is the most optimal utilization of your scarce resource, which is spectrum, to communicate information over it. This was really important for Bell Labs and AT&T long lines back in the day because they spent billions of dollars to build wireline infrastructure and carrier networks to be able to make a phone call from New York to LA. Right now, everything's all IP. Back then, they had to put transmission towers every 30 miles to move that data. And they had to worry about this all the time. Now we don't have to worry about it. But what gets really interesting is that, so everything's in software, right? And we can get down to the waveform level to control this device and what it receives. What if I could also make this device talk back? Everyone's talking about how 5G is great for bidirectional use cases, but ATSC 3.0 is still a broadcast protocol. About 2 months ago, the same engineers that figured all the other stuff out, they figured out how to make these devices communicate back in that same forward block of spectrum. What that means is now any ATSC 3.0 capable receiver that complies with this specification can be an addressable device and communicate back. So hypothetically, if you're a company like Google that supports a license acquisition and conditional access product like Widevine, that license key exchange process is very little data. And that transaction can occur now without you having to be connected onto the network. So there's a lot of interesting use cases that come out of it. And going into some more detail is there is 2 fundamental ways of distributing content in ATSC 3.0. The one that you will probably hear the most about is what's called route dash. So this is what's called a layered IP distribution model that essentially is a dash manifest MPD delivery, and people are trying to be really smart and support live distribution use cases over this. Again, the problem comes in is that this is still a noisy communication channel. You don't ever cross over the Shannon limit because sometime there will be noise in the signal that prevents you from receiving the content. The problem with dash is, though, in this model, by using route as ALC for delivery of that object, and dash doesn't understand the media-aware representation of the transmission unit. So this is where the ATSC committee went kind of a little rogue and adopted a standard called MMT. It's called MPEG Media Transport. I had never heard of it before this. I couldn't find anyone else outside of the Koreans who had done anything with this. And essentially what it is it's a fragmentation-aware transport layer that essentially in ATSC 3.0, as you receive content from the broadcast, it's fragmented, and the de-encapsulator and the player know every piece of that transmission as it comes in, rather than you just playing the ISO BMF boxes accordingly. And it's really, really interesting because now you can support low latency distribution use cases in lossy transmission environments because there's more intelligence on the de-encapsulator and the decoder. I'll go into that in a second, because I know super complex. But when we start putting these pieces together, that's all super nerdy stuff. This is where the cool stuff is going to happen. There's 2 standard formats, or two portions of the specification. One is called application signaling, and one is called interactive content. They realized where convergence was starting to come, when they wrote this up 3 or 4 years ago, and they saw that technologies like WebSockets can allow for bidirectional and asynchronous communication between a hosting app and essentially a companion app, or in this case, in a TV ecosystem or a connected device ecosystem. And then they said there's some really great graphics capabilities that have come out here. So why don't we support not just compositing, but also transformation and capabilities on top of it? So essentially, the next kind of wave of, now that we got all the baseband infrastructure working, is by being able to control and interact with the forward broadcast and being able to provide those experiences through the over-the-air transmission, I think there's going to be a lot of interesting use cases where really, really smart people can start building OTT experiences over OTA. And what that means is I'm no longer having to distribute out my content in lower qualities because everyone in a market will get the forward transmission, which is going to usually be a HD 1080p 60 rendition of content. You're no longer getting ABR ladders. You're no longer getting buffering windows. Your device is going to be smart enough to be able to rebuild that on the fly or have a caching capability. If you guys have seen the Amazon Recast, that's a great use case where it has a terabyte of data next to it. And because this is all IP, those objects can live on your DVR device, and with conditional access on top of it, now you don't even have to wait for that content to come through because it's already in your environment. So when we start putting these pieces together, there's been a ton of investment, a ton of research and development, and a ton of work done on the RF side, the plant side, but that means nothing to us in here. So 2 months ago, I was out on the East Coast, and I had this guy with me, and I said, now I can start touching it, I can start feeling it, I can start seeing what this looks like, because this just gives me back an IP data stream. There's nothing special about this except translating all that technical detail to giving me IP data flows. So if you've ever used Wireshark before, or TCP dump, you have everything you need to take this, all this stuff, into a completely virtual environment. So the last piece of this is that I have started an open source project about 2 months ago with the objective of demystifying ATSC 3.0 and getting a software engineering community more involved into it. Because ultimately, if we can help make the technology the facilitator, there's a great opportunity in here. And so I'll walk through this just in a few more minutes, but every time I go to a market that has ATSC 3.0 forward transmissions, I have a second laptop that I take PCAPs of. I have those checked into GitHub. Inside of the ATSC 3.0 specification, there's service location table acquisition, there's MMT de-encapsulation and service level signaling, there's ALC route object reconstitution, and then dash replayback. There's ISO BMF remultiplexing into the audio and video assets elements into one ISO BMF data stream, and then I pipe that through FF Play. So what it means is that all in software on my laptop, I can be a virtual broadcaster and replay content. So just to give you an idea, when I started building this out, I didn't really think I was going to be able to get this far here. But so for the purposes of this, I have been running this for the full demonstration on a, oh, sorry. Let me switch screens. So for those of you who love CLI interfaces still, so this is a breakdown of the IP data flows that are coming from I've got a virtual machine that's just running PCAP back through here, a TCP dump replay of, this was a transmission that I captured from over there, I think. Just pull this one out full screen. And essentially, I am just replaying this, this PCAP here. Again, I've got samples from a few different events, and these are just a few steps to be able to replay essentially what would be a forward transmission here. So for this file, if I wanted to play something else back, I've got a set of data from, I was in Santa Barbara a couple weeks ago, so I can pick this one up. Essentially, I will do, so let me close this out. But just for the purposes of this, while I was doing my presentation, essentially this harness here pulled about 1.75 gigs of data, 1.4 million multicast packets. Forget the missing packets, that's a rollover number, so that's not really fair, but it was running while I was doing my presentation. And again, this is all written in C with the exception of Bento 4 as a library to include for the ISO BMF box reconstitution, but that's not needed for essence elements directly. So I'm just compiling the library. I'm going to pick up now, and the first thing it does is it does essentially the SLT lookup. It finds out what the transmissions are in here, and right here it says this is ALC, and I can pick through the TSIs and TOIs. In this use case, behind the scenes, so I'm going to pick it to go to the service ID of 1. And again, I haven't done this lately, but so behind the scenes, route is essentially just delivering those individual objects. So when I look at this, what I have is essentially I've got a signaling payload here, which is the EFDT, which tells me what the objects are inside from the layered delivery. I've got init boxes here, and then I've got my media fragments here. So in this case, I'm going to tell it what my, I know for this one what my specific video and audio are. So I'm going to say I want to do the video as this TSI1, and the init box is this object. I'm going to do my audio is 2, and now this is all part of the specification for service layer signaling. I just haven't completed it on this, but if we do this right, just make sure it didn't.
Thousands of hardworking families.
So it's on my other screen, but for the purpose of this, you're watching ATSC 3.0 with route delivery on here. Let me just switch over to mirroring my displays. And it is a over-the-air capture that I made with the red zone receiver. So this is all code that's checked into GitHub, and the PCAPs are checked into GitHub. So kind of my ulterior motive in going through all the hard parts of this early part of the discussion about what is ATSC 3.0, why is it such a game changer, and how does that help everyone break down the barriers to be able to adopt this? My hope is that what you can see here is what will be coming to market very soon. Right now, this is probably a little bit higher than it should be, but 6% is CPU to reconstitute, in this case, this is 16 megabits of forward multicast delivery. So that's not too bad. It's not super optimized, but again, like no drops, no fragmentation, no issues here. I'm gonna drop out of that one. So that was route. Again, non-real time for distribution use cases. Let me switch over to another capture, which is going to be MMT. So MMT is a bit tricky to find over-the-air transmissions in the US. I do have some associates who worked on the Korean system, so they provided me some packet captures for reference material. But again, this is recompiling the full payload of this project, all the dependent libraries. Again, a very similar structure, except that in the service location table, it's going to say MMT here for the service. This is wired up to the service level signaling. So when I tell it that I want to switch to MMT mode, and I select the service ID 3, it knows everything for the audio and video packets. I hit play. The right-hand side is the media-aware fragment information. There's a lot of details in this. It's incredibly, it's down to the essentially the sample level of the ISO-BMF boxes that you know whether you have a linear transmission or you're missing data. So it's quite impressive when it comes to recovering any data loss or transmission. So you can see down here, I'm monitoring each one of those individual flows. I lost maybe 3 packets of data, so 1,400 bytes times 3. And because I know it on that granular level, I'm able to recover this. Rather than in scenarios like with route, you would lose that whole GOP. So this is really, really important to go back to that use case, because route is built for a broadband request for object recovery. MPU is built for a live linear distribution use case where your latency is measured in milliseconds, and you cannot go out to a content delivery network to request the missing fragments of data that come through here. This one's a lot lighter in its distribution. It's only 400 packets a second. But to give you an idea of what this looks like from a specification standpoint, again, all of this is is either standards that are published via the ATSC 3 website, the ATSC standards. All the details, screenshots that I have from here are in this. Additionally, there are the ISO-BMF specifications and one other specification for MMT, which is ISO 23008-1. I have included the relevant portions of my code of what's imperative in it. But essentially, this document has been under development for 10 years. I have asked everyone I know where there is code for this, and nobody had any. And what I'm hopefully showing you guys right now is this is playing MMT back right here. Behind the scenes, it's reconstituting everything. It's doing all of the pieces that are inside of the specification in real time. This is the data behind it. Essentially, the way that MMT works, because it's media aware in the ISO-BMF model, is again, you'll see the same kind of structure and architecture from this. You've got assets, you've got all these other pieces, but you've got presentations. But ultimately, what it comes down to it is you've got assets that are comprised of a MPU, a media presentation unit. And then when you reconstitute those all together, you essentially reconstitute this ISO-BMF box. So there's 3 different types of fragmentations that it supports. There's the init box with the F type. There's the movie fragment metadata, and then there's the actual track data. So if you ever are really can't fall asleep one night and are interested in this, it gives you all the technical details you need to do this on your own, except that I already have it. So this is really exciting, because I didn't think it would only take me about a month and a half to, from Greenfield, take not just a 80-page specification here, but cross-reference it with the 1,000 pages of ATSC 3.0 specification and get this data out here. So essentially, when you look through this, again, this is all IP data. So if you use Wireshark, we can walk through here as it's playing back, because I am playing this through a virtual interface. Let me just start this real quick. And what I have here now is, this is the raw data flow. Now, I kind of lucked out, because one of our partners that we have, they give me a protocol dissector inside of here, which was really the saving grace. And they have not released it publicly, but again, my source code, the functional implementation is on GitHub, and I'm more than happy to socialize this out. The head of master has what you are seeing running right now. If you are interested in the MMT side, this is in the MMT MPU parser, and everything you need to re-implement this, again, as in C code or cross-target or cross-compile, that's really, really exciting, because opening up the complex world of hardware engineering from broadcast is what people like Darren and Andy do, with people kicking and screaming every day because they don't understand why we want more agility, more flexibility, more dexterity in the fundamental technologies. And let me just see if this finishes loading up here. So it has essentially the MMT protocol representation here. Again, we will see that inside of the MMT media presentation unit, this is a fragment type of 2. It contains the sample data from it. And then there's a number of great open source tools like Bento 4. And if you have not used them, I highly recommend taking a look at it.
Bento 4?
Yes. It's Bento 4. And if you've ever wanted to see what was inside of a ISO BMF MPU, essentially everything you need to cross-reference in the ISO BMF specification, this tool will give you the data output to see. So this is one of the reconstituted fragments playing back through FFplay. And all the boxes are here. It assists with you being able to recalculate samples and durations and adjust things accordingly. Very, very powerful if you have not had a chance to use it. So just to wrap things up, I really appreciate everyone's time to listen to kind of the future of where things are going and how I'd like to help facilitate that. So as I mentioned, the core of that C code is checked into libATSC3. There's not a strong build system behind it. You will need to target your own Bento 4 library build, because that portion is GPL code. So again, this is all open source right now, but I also have MMT PCAPs for replay. 2 other things that are also potentially interesting for this group here is, if anyone has ever streamed HLS through FFmpeg to a RTMP destination or MPEG-TS destination, PTS discontinuities have been the bane of my existence for years. On my professional side, we do this all day long with Facebook, and we do 200 linear streams to Twitter, from HLS-based origin resources out to RTMP distributions. If there is a gap in that PTS discontinuity, at least the head of FFmpeg earlier this year did not have support for supporting that discontinuity. I have a branch out there that fixes that if you're interested in. And lastly, for anyone that's in the monetization and technology side, is I have written a SCUDdy35 injector. So if anyone's familiar with SCUDdy35, there are a few great tools from Comcast, their open source team, to provide SCUDdy35 decoders. But I've never seen anyone provide outside of TSDuck released theirs late last year. That was the first implementation I've ever seen. But TSDuck is really designed for transport stream tools. Instead, this is a Java library that you can build your own, essentially your own program segmentation descriptors, your own SCUDdy35 messages across. So I'm going to just run this right here. and debug. And if you haven't looked at Scuddy 35, it's ironic that the JW Player team is having their meetup group right now, because here's an example of the Scuddy 35 payload output for a base 64 encoded Scuddy 35 message, which you can put into a mux it into the manifest and trigger a client-side add insertion all the way through using an industry standard form of add triggering and decisioning. Scuddy 35 has been in the cable industry for the past decade. It's what controls every single insertion you see. We brought it all the way to the client side here, and just this little piece of this payload data is all you need to be able to trigger your ad break for digital distribution. And this is really an interesting use case and model, because you can mux it into VOD HLS resources or live linear HLS resources. So when all of this comes together, there's a ton of opportunity to put this information in a non-proprietary and industry standard and adopted data payload and representation. So this is the example of the decoder of that, and I see I've got in this case it's a program start signal, but I can provide additional metadata and descriptors.
So that base 64 decoder is your decoder is there in the GitHub?
The injector port code, so there's two parts to Scuddy 35 usually. There's the splice, essentially the downstream splice on the distribution side, which preempts the linear output and then will insert a essentially the preempted advertisement is what the splicer will be responsible for. So there's the time that the Scuddy 35 Q command is injected into the transport stream, and it has a PTS time of when the splice should occur, and that's usually an IDR boundary. It knows the duration, and then it will come back. So that's the decoder side. But creating those messages, only a few people have done that, and it's usually Imagine, and it's usually Harris, and it's usually the MSOs that do it. But because partners like DFP see the value of metadata in their ad marketplace, now we can trigger client-side ad insertions through JW Player. And additionally, if anyone uses DFP for the ad monetization, the Amazon Elemental team has their media tailor system, which also uses Scuddy 35. But this is special because you can provide programmatic data of what someone is watching in that feed into the ad decisioning process. So if I'm watching, let's say, Cheers through digital distribution of my OTT device, I don't need an out-of-band command anymore because it's in the payload for it. And now your ad decisioning server can essentially do reconciliation and revenue reporting like a traditional linear traffic system. And you can also use that programmatic data for programmatic creative buys, and then also, so I can buy into a specific show or episode now for digital.
With downstream with your ad target.
Yeah, exactly. Through the right ad decision structure, but Google has started working on this, and if they've adopted this, there's got to be a lot of other opportunities to come together, not just with Google, but with Media Tailor, with other private marketplaces, Freewheel. The more metadata that can be provided contextually in because remember, the challenge comes in server-side ad insertions. You can't provide real-time metadata of what someone's watching in like a linear feed. Like, you can trigger a client-side ad break, or you can trigger a out-of-band command from like an OTT experience. But now the ad decisioning server, as it's playing out that VOD content, will know exactly the metadata that was injected by the distributor, or for live content, they can make decisions without having to send additional metadata. We can talk about it later, Andy. But this is going to be super interesting because it essentially makes complex traffic systems and automation that need to know programming data with ad buy data. You have it now. So I know there was a lot to go over. And is there any questions I can help answer? So,
Question was what other markets other than Phoenix?
yeah. So, Santa Barbara, what we're finding is that PBS is very interested in this use case and model because along with the technology that's applied from the distribution side, that means that it can also change their facilities' operational costs to be able to move to the cloud substantially. And in a business unit like PBS, while it is publicly funded, that is every year keeps walking down. So they have to find a way to drastically reduce their cost basis for operation. And a lot of what PBS does is distribution. If we can move all of this to a cloud-based model where those data streams are sent out to individual markets because it's IP multicast, all of a sudden then this is what we start thinking about of a next generation broadcast platform where it's not racks of equipment, it's not virtual servers, it's not edge devices, it's the opportunity to be able to produce this content with a multicast network overlay, be able to distribute it out, and because it's so flexible, the value of the spectrum that is available now, which didn't ever exist before, now other players can share into that market or other partners can buy into that market. If I'm a content delivery network, maybe there's a use case there. If I have a station in a market and it's a hard market to be in, I can then sell that spectrum. I could sell access to the data transmission of it. I never let go of the spectrum, but now I can extract value out of it. And I think in 5 years, the smart guys on Wall Street will figure out a quantization model to make money out of it. Because all you're doing is dynamically hedging. Is who's going to give me the lowest cost for distribution and who can I get the largest reach for that audience in? Because remember, you're sending one copy out. In the case of Seattle, that's probably one copy to potentially 250,000 people in a couple mile radius. If you're driving your car and it needs a firmware update, do I really want to send out 10,000 copies of the same piece of data? So there's use cases and models in there that are very interesting. Again, it's not bigger pipes, it's smarter pipes for distribution.
How much of this is available in DVB?
In what?
In DVB.
So from the DVB-T2 side, they have a lot of work done on the what's called HBB, hybrid broadcast broadband. That set a lot of the foundational use cases and objective into it. The problem is that again, when you put hardware engineers and solutions and you put consensus building into it, they will add in a dozen different ways to do things. So the fundamental problem with DVB-T2 is A, it's not nearly as close to the Shannon limit and the efficiency that potentially the modulation parameters inside of 3.0 can give you, because in that PLP scenario is I can have it can have different modulation codec responsibilities that say I can reach my full market with one tower, but then I can carve off, maybe that's at 10 megabits on there, but then I can carve off another overlay in that same spectrum that's maybe only 1,000 feet, that's at 50 megabits, right? So you can build these physical layer pipes essentially in this virtual spectrum. The problem is that DVB-T2 relies more on GRE, and then the output of that generic routing encapsulation becomes IP. It's not IP in the transmission side, which is kind of the mistake. ATSC 3.0 isn't perfect, but it's just a prefix for what's called ATSC ALP, so ATSC application packet. I forget the exact terminology, but it's essentially just it's an RTP box prefix on it. The hardware, when it processes it out of here, that drops it off because that's just the physical layer side, and you just get an IP multicast stream. I think there's too many other encapsulation sides that are in the physical layer side. We do work with a partner that is in Europe, and they've had some really great success with the DVB-T2 side and the HBB. But again, the spectrum efficiency and extraction for new use cases for object delivery are really the interesting part, and relying on software-defined networks and software-defined radios to facilitate that in use. that's really hard when they've got now 5 years of legacy out there and new use cases. We're going to be in the same spot in 5 years, obviously, with the exception of that bootstrap. So that preamble, that signal in there. Now, devices that don't know how to handle the following waveform, maybe it's not QAM, maybe it's not, maybe it's not QPSK, maybe it's some other derivation that some really smart people have figured out with multipath coherency and interference and things like that. DVB-T2 can't ship new products in market without fundamentally making a material modification in the RF layer of the spec. The bootstrap will provide a versioning info for devices that can process that signal waveform in software and be able to then handle it. So micro extensions of it can be implemented on the waveform level rather than on the application level, if that makes sense. So closing that Shannon curve means you extract more value out of it over the long term, and you can provide low power wake up experiences like 802.11.15 or Zigbee. Now, your device doesn't have to be listening to something in a 10-foot radius. It can be from a forward transmission because it knows how to wake up just on that bootstrap portion of the packet. So there's a lot of interesting use cases in the IoT, especially facilities management, when you tie in that DRC side now, because you can build a completely disconnected IoT network just using the forward channel for command and control and the return channel for telemetry back. And maybe it's only 30 bytes of payload you need back, and you only need it once every 12 hours. You can do it with LTE, but it will cost you a lot in battery and power. And so there's a lot of interesting models when this comes together to really change how systems, communities, and people and data moves through broadcasts. So.
And presumably the price point of these software radios will, you can get software radios, obviously not like that one, but
Yep.
for other applications that are, $100 if that, right?
Yeah, exactly.
So over time, that's going to come down.
Yeah, and the GNU software radio, that's really impressive. Additionally, I don't want to speak for Sinclair, but this is public knowledge. We have a strategic joint venture with a company in India called Sankhya Labs. The first generation of these chips were fabbed out at CES, and we have made verbal commitments to subsidize up to 1 million of these software-defined radio chips. And again, these can do not just 3.0, they can also do DVB-T2. And the constellations align and the timing aligns that with a different guard interval can also do 5G. So there's a lot of interesting use cases that come out of it where now you're not paying to upgrade the baseband side of your phone, or you're not paying to upgrade capabilities of the next AT&T 5G network that's not really 5G right now because it's just a microcode update to the software-defined signal analysis waveform processing. So.
Any more questions?
Yes, Andy.
Can that device using those new chips go 10 feet at a low bit rate?
So yeah, so I was so at a low bit rate.
For an Internet of Things application, or
I wouldn't see. If you're talking on the reception side, absolutely. I was driving around in Baltimore at like 80 miles an hour, and I could still get a baseband lock on this one. Again, the interesting part of what you just asked is, though, inside of the specification, again, super technically nerdy, but essentially the idea is that in the PLP, so in the physical layer protocol side of this is that you can define those virtual channels essentially in that one block of here. There's up to 64 different coding parameters that you could have in a forward transmission. So inside of this, potentially you could have just a use case that models a PLP that is just at a super low bandwidth for signaling or IoT use cases, and I'd have to go through the math, but the idea is that they provide a breakdown of all the different modulation schemes and what the utilization is on here, and you can dynamically configure those from the transmission side. This is not a forklift upgrade. This is a core part of the network infrastructure called the scheduler. There is a piece of software, it's an A337, I think, no, hold on, the STL. So you have the command, you have the control points in the physical RF layer, and then you have this scheduler studio transmitter link system. This is responsible for all of the essentially what would be traditional TDMA access in provisioning into that data distribution and delivery. This thing is incredibly powerful in being able to schedule any piece of data that has to move through the network. And this is this use case, Andy, where I can literally make this like the lowest bit rate distribution and have the widest coverage for it.
Any piece of data in any direction, even backwards if you want.
So again, the backward side is still under hardware development. The specification aligns for it very, very well. And we should talk about that, Andy, offline, because the DRC spec is published on here. It is incredibly complex for the mathematics on here, but this is a 323 dedicated return channel. And it will have the answers you need, but I stopped reading at here when they had to talk about convolutional codes and hole punching in here when the polynomial equation literally ran off the page. So, and I know you could probably read it, but when I started see equations like this, that's where I say, no, thank you.
So we have a question from somebody who's watching the live stream, who's watching this in favor of everything in favor of Netflix, he says. So his question is that about the SCSI-35 in manifest triggering client,
Yep.
Client-side ad calls. So JW Player implemented that plugin that you showed, but is there something out there that can fix the problem that happens in iOS where you can't access the HLS tags in the manifest, making that implementation almost impossible?
So you might want to reach out to our good friends at Apple at that one. Unfortunately, so Apple should allow you to, inside of the ID3 metadata tag, you should still be able to emit those events. At least the last time I did low-level development in Safari. So there's the,
I think he was specifically referring to iOS.
to iOS or Safari?
Yeah, well, he says iOS on Safari.
Yeah,
It might actually be something that I connect you with him directly.
Yeah. There was I have seen it come through, but there are other use cases that you can force segmentation boundaries to be able to trigger events. So
Okay.
that way, by preemptively terminating by providing an EXX endless tag, you can support that. But Apple's implementation of HLS decoding has always been a very, very closely guarded secret, even though that they pretty much invented it. So again, I would be more than happy to take that offline, but it's not perfect in there, but there would be a great use case to say we would like to support that all the way through.
Cool. Well, Justin, thank you so much. He's been up, I think, about 20 hours at this point.
Yeah, coming from Phoenix at like super early yesterday, and so it's been a long couple days.
And so I guess the main call to action is the project.
Yeah, so one of the things I think would be really interesting is, David, working with you is this model and this use case, because I literally work across the street over at our Como building. I would love to also consider doing a monthly hackathon and bringing some of these pieces together, because this is really easy to get up and running. And once you get up and running with content and you can actually see things, and once I have the other parts to be able to start bringing through the A337 and the application delivery, now what it means is we could literally spend an afternoon here, write an OTT app for OTA. And I think that'll be really, really cool. So,
Oh, I agree. That sounds great.
yep,
Thank you.
cool. Great, thanks.